So in this video today, we're going to be going over related rates. So usually related rates is the hardest, or not the hardest, but the hardest thing to get when doing derivatives. It's pretty much hard for people to understand because it's pretty much real world applications. And that's the reason why people have a hard time just understanding it, is because you need all the differentiation rules that you learned over the past, 4 or 5 weeks. And it's usually the last section in your calculus book, in the derivatives section, because you do need to know all those rules for differentiation, because they're really important when finding, when trying to find something related to something else. And these real world applications related rates is pretty much why you're doing all this. It pretty much explains why you learn derivatives, how they relate to the real world applications, like how much is something changing with respect to something else, pretty much. So in the first example I got here, it's pretty much what most people learn, is how fast a tub is filling up with respect to time. So you want to know how fast is the water level rising if the water is filling the tub at a rate of 0.7 feet per minute. So this is our tub, and that's our water. We know it's filling up at 0.7 feet per minute. And the base of this bathtub is 18 feet squared. So we know to find the volume of anything, it's volume is equal to base times height. So what we're going to do is we're going to let the height equal 18, the base is equal to 18. So we're going to let the height just be the height. We're going to let the base equal 18. So if we do this all out, we're going to get 18 times h, which is going to be V is equal to 18h. So that'll tell us the volume of the tub, but we want to know how fast the tub is filling when it's filling at 0.7 feet per minute. So the first step of solving this is we know V is equal to 18h. So what we do is we take the derivative of all this. And what you get is dV dt is equal to 18 times dH dt. And so you want to know how fast the water level is rising. You want to know how fast this is rising when the tub is filling up at 0.7 feet per minute. So we know the volume is increasing at 0.7 feet per minute, so we could plug in. So dV of dt is equal to 0.7 feet per minute. So 0.7 feet per minute is equal to 18 feet squared times dH dt. And now you can pretty much see we're going to solve for dH dt because we want to know how fast the water level is rising, which this is the base, and this all right here is the height. You want to know how fast it's rising when the base is equal to 18 feet. So you just solve for 18 feet squared, which is just 0.7 feet per minute divided by 18 feet squared, which is equal to dH dt. And so let's just erase this up here. And if you type that in your calculator, you will get 0.039. So dH dt is equal to 0.039 feet per minute. So the water level is rising at 0.039 feet per minute. So the height of this bathtub is changing at 0.093039 feet per minute. That's what we wanted to find. This height right here is going up at 0.039 feet per minute. When you're pouring, you could just say this is a faucet. Pouring some water out. And it's pouring it out at 0.7 feet per minute. And we pretty much solved it. So we know how fast the water level is rising when we're pouring 0.7 feet of water per minute in the bathtub. And we have an 18-foot bathtub. So now we could do another example problem. So we're going to get away from rectangles now. And now we could consider the following. We have this oil spill, oil slick, and it's expanding out at 2 meters per minute. The radius is expanding out at 2 meters per minute. And what we want to know is, one, we'll just go step by step, how fast is the area increasing when the radius is equal to 25 meters. So what we know is the area of a circle is pi r squared. So now we're just going to do the same thing that we did on the last problem. We're going to take the derivative of all of this. So then we're just left with dA dt is equal to pi times dr, r times, well, we'll go 2 pi r times dr dt, and r is equal to 25. And it's expanding out at a rate of 2 minutes per minute. The radius is expanding out at a rate of 2 minutes per minute. So the derivative of the radius with respect to time is equal to 25 meters. And now we got enough, so we're finding out how much the area is changing when the radius is equal to 25. And the radius is expanding when the radius equals 25 meters. So now we got our equation. So it's 2 times pi. We just plug in for r, 25, or not 25. Yes, 25 actually. Hold on a second. No, you don't. This isn't 25, this is 2 because it's changing by 2 meters per minute. Times 2 meters per minute. So dA, we'll just erase all this up here. dA dt is equal to, when we plug all that in our calculator, we get 100 pi, which is equal to 314.16 meters squared minute. That's how fast the area is.